Welcome everyone. My name is Peter Gorm Larsen. I'm professor at Aarhus University. And since many of you probably don't know me, I added a slide about myself because I have an unusual profile being a professor in the sense that I spent 17 years in the private sector before going back to my technical roots. And I have been working on things all the way from, as you can see, aircraft, things like the one you see up there, it's F-35, as well as medical. That's next one is from a patent I was involved with, as agricultural equipment. But mostly what I'm doing these days is that I'm working with digital twins. But today I'll mostly be talking about what is RoboSapiens, why did we start that project, and give you a little bit idea for that. So if you know about robotic systems, many of them need to be certified. And if you have things that are being learned, at the moment there is something called a machinery directive that gives limits to you and say, well, you're not allowed to just reuse this further on. So what you see over here is something called MAPE-K. MAPE-K essentially is an approach to try to do autonomy, to try to autonomously update things. However, this is not safe if you just use the standard approach to this. So what we are trying to come up with is a slightly changed thing. It's called MAPLE-K, where we have an extra step where you kind of monitor, you analyze things, you do a plan, and then before you execute that plan, you try to say, well, is it actually a legal plan? Or are there safety constraints and safety problems with this? So that's where the MAPLE-K is coming in. K means knowledge, and K is the knowledge that you have from about where the real system is. But in addition to that, and that's the second innovation we are trying to do in this project, is that right on top of the control software that you have for the robot, we have something we call the trustworthiness checker. Something that's checking dynamically if anything is wrong. So I'll come back and say a little bit more about that in a moment. The way this project is constructed is that we have a work package that deals with trustworthiness. We call it work package 3. On top of that, there's a work package that kind of takes care of the analysis and learning things. This one is actually led by Tassos that just introduced me here before. And on top of this, we have a work package that's trying to kind of give us the foundations that we use to build all of the approaches we have here to make sure these things would be certifiable, based on a methodology, an architecture, and ways of integrating things. And then we have 4 case studies that we use to operate all of this. And finally, we have a work package that takes care of dissemination and exploitation, just like the event we are having here today. You're going to hear from the work package leads of each of these, trying to give you more detail of what's happening there. But in a nutshell, you can see these green arrows that are pointing upwards here. They're trying to say, well, if we take things from the physical system, we try to monitor, analyze, and learn things before we try to do a plan and try to validate the plan before we actually execute it. So we have 4 objectives of this project. One is to try to look into how can we enable the control of robots with taking into account that you have unprecedented structural system changes and also changes in the environment, things that could go wrong that we didn't really know about when we actually designed the robot in the first place. Secondly, it's a matter of ensuring safety of the robot as well as the environment around it, including the people that are there, both during the adaptation, but also after the adaptation we would do to the robotic behavior. The third one is to essentially try to actively reduce the task uncertainty. Because there are uncertainties in the environment, there are uncertainties with respect to the data we get from different kind of sensors, etc. How can we actually do that and still do safe adaptation of our robots? And finally, we want to assure what I call trustworthiness. We can actually trust that if we are doing deep learning of things, that the architectures there are actually going to be working and operational and safe to have in our environment after we have done this adaptation. So the key innovations I've already mentioned, these are the standard things. We are putting in the L stands for legitimate to say, is it legal, this thing? And in a sense, you can say it's a matter of trying to record what are the safety constraints we would like to have, given some assumptions that these assumptions need to imply certain properties. So that's what we are doing in the legitimate phase. Now, when we then look at the trustworthiness checker on top of the real robotic software, we have also checked, we're also checking the assumptions we made when we try to check whether the plan was correct. Because if the assumptions are wrong, well, we can't trust it anymore and we would have to stop things. So the extra additional challenges are our uncertainties. And you'll also hear more about uncertainties and how we can identify and eliminate those uncertainties. So one of the things we have in here, in part of the architecture thing, is we have a RoboSapiens adaptive platform. And this essentially is trying to put a layer in between the place where you have the autonomy action, it could be in a cloud, and then the actual operational software. So it's trying to gather knowledge and to handle that in a proper way in order to handle adaptations and diagnosis that you do during your execution, and then ensure trustworthiness of the knowledge and the actions. So that's what this robotics adaptive platform that you will probably, RoboSapiens adaptive platform that you'll hear more about a little bit later. Overall, we have a concept where we go from concept to design to realization. And many of these steps are actually operationalized, automatic. So you don't need to manually move from one model to another model to some code. There are automation that's being used. You'll also hear more about that in here. And you can see some of the work packages. These are the 4 technical work packages. Where are they involved in these different actions? So we have also produced a number of additional open source tools that are used to actually do uncertainty estimation, try to help and learn different things about the robotic system. I will not go into detail with any of these. You're going to hear more about this approach in one of the other presentations. To understand for you what the project is also doing, we have 4 industrial case studies. One, you will see later, is about how can we get a robot disassemble a laptop. So imagine you want to reuse a laptop or parts of the laptop, you may need to refurbish it somehow. Well, how can we get a robot helping to do that? Today, there are few companies doing this, and they are doing very, very much manual labor. How can we get robots doing that? The second one is a matter of trying to look at ship motion prediction. So think, can we have a ship with nobody's actually sailing? We are having an autonomous ship. There are test facilities in Norway we are actually able to experiment with that, and that's one of the things we have here as one of the case studies. And then we have a case study that is looking into, can we actually dynamically look at the risk model of operations that a robot is doing? In this case, it's for manufacturing, so where you have what I call cobots, a robot that's working close to a human being, and then saying, well, can we actually try to take into account where are the humans, what part of their body is close to the robot, what's the potential danger of that? And finally, we have a case study which is about robot navigation, where robots are moving around in some facility and needs to navigate as a fleet of things. For all these 4 case studies, you're going to hear different presentations. Now, if I look at what have we actually produced so far, we have established a baseline survey of how can you do this MAPE-K autonomy thing. It's being submitted for publication, hasn't been published yet, but it's a promising result, I would say. We've suggested this MAPE-K approach for doing safe self-adaptation. We've suggested the trustworthiness checker doing based on something called runtime verification, and which we dynamically can change things. We have produced the RoboSAPIENS adaptive platform architecture supporting the framework, and there's a toolkit for that. And then we have produced a large collection of tools that support the MAPE-K approach. Then we have done automatic transformation between different formalisms from the conceptual, the design, the realization stage of things. And then we have suggested 2 new academic case studies. In addition to the 4, let's say, industrial size ones, we have 2 smaller ones that you may see in some of the presentations in here. And then we have demonstrated the initial technologies on the industrial use cases. The technology is still under development, so what you'll see here is work in progress. But by the end of this year, we'll be finished with the entire project. And we have published quite a lot of publications so far about the research we have conducted. More are in progress. So one of the things that I want to tell you about, also the people who are online, is that we have what we call robotics follower group. And if you wish to actually see more about what we are doing, it's possible to subscribe to this. It's free of charge. It's a possibility to actually meet some of the people we have in the community, in the project here, and actually try to have a discussion with us about some ideas you might have for robots and AI. So with those words, I think I will stop my presentation and move on to the next one.